Hi guys, welcome back. I hope you enjoyed your weekend. So we're going to be talking about photochemical smog and acid rain. This is module 47. It's a pretty quick module, so we'll try to get through it quickly. And if you have questions, let me know. Okay, so our learning objectives for today. After reading this module, you should be able to explain how photochemical smog forms and why it's still a problem in the United States, understand thermal inversions, and describe how acid deposition forms and why it has improved in the United States and become worse elsewhere. Okay, so photochemical smog. Just a reminder, we talked about photochemical smog in our last module, module 46, but photochemical smog is smog that's dominated by oxidants such as ozone. So this module is really going to focus on ozone, the formation of ozone, the differences between tropospheric and stratospheric ozone, and sort of what that means for pollution. Several pollutants are involved and in the formation of photochemical smog, and they all undergo a series of these transformations. And like we said, when we see the word photo, we should think of sunlight. So sunlight is one of those, things that helps to contribute to that transformation, as well as water and VOCs. And remember, VOCs are volatile organic compounds, and those really come from things that have really pungent smells or really fragrant. So things like gasoline or dry cleaning fluids, or some natural plants that have a really strong smell to them, are all VOCs. We have both anthropogenic and natural VOCs. So ozone, what really is ozone? So you probably know of ozone, or O3, in reference to stratospheric ozone. And stratospheric ozone is a really good thing. It's actually what prevents us from getting too much UV light from hitting us. So we know UV rays can be incredibly damaging to biological molecules, so things like us. So the ozone is really important in preventing that from reaching us, and also keeps us a little bit cooler here on planet Earth. But tropospheric ozone that forms in the troposphere, and a reminder, troposphere is the ozone, or the layer of the atmosphere, that is closest to us, it's closest to the Earth's surface. Ozone that forms in the troposphere is actually really hazardous. We don't want tropospheric ozone. This is actually one of the things that leads to photochemical smog. So let's take a look. So this looks messy, but I'll try to explain here. So here's kind of how ozone could potentially form in the troposphere. So we'll look at this first image. We've got things like nitrogen dioxide. Now, nitrogen dioxide, just as a reminder, is something that comes from the combustion of fossil fuels. So that's something that can come from your cars, or energy producing power plants that are burning things like coal. So NO2 happens to be in our atmosphere quite a bit. Now what happens is that NO2 gets broken up into NO, nitrogen oxide, and one oxygen. And this separation happens as a result of the sun. So remember, photochemical oxidants require transformations in the atmosphere, and sunlight is one of those things that drives those transformations. So we've got the NO2 that's being separated by sunlight, and that NO and O, that excess oxygen, is then going to combine with O2, and O2 is something that's naturally abundant in our atmosphere. That's oxygen. It's the byproduct of photosynthesis, and it's what we breathe, so we hope there's an abundance of O2 in the atmosphere, and those are going to combine and give us O3. Now notice the time of day this is happening. It would be when the sunlight is most strong, or when we're during daylight hours, essentially. Now in this next one, as the sun is setting, as the sun starts to go down, we actually see ozone depletion. This is when the ozone actually breaks down. So we create ozone during the day, but oftentimes as the sun starts to set, we actually see it starting to break apart. So that ozone combines with that excess nitrogen oxide that we just said was floating in the air from up here, and that's going to, as a result of there not being anything for transformations, reform to oxygen and NO2, which is what we initially had. So we kind of go back to where we were. This is what would normally happen on a day. Now, here's what's happening if photochemical smog is being formed. So we have the same sort of concept here, where we have this excess of NO2, again from the burning or combustion of fossil fuels, where we get the NOs and the oxygens, and we see that creation of ozone. So that's the same as that top image we just saw. But additionally, with those excess NOs, if we have excess VOCs in the air. And like I said, this can be from gasoline that gets evaporated off cement. It can come from dry cleaning fluids, plants that have a really strong pine type smell. Those give off natural VOCs. Those natural VOCs are going to combine with your nitrogen oxide, and those are going to create photochemical oxidants. Again, all of this transformation and combination is happening as a result of the sun. And the combination of O3 and those photochemical oxidants is going to give you photochemical smog. So when VOCs are present in the atmosphere in large quantities, not only do they contribute to photochemical smog, but they prevent the breaking down of ozone, right? So we know we aren't able to break down our ozone, and as a result, we end up with something called photochemical smog. And remember, photochemical smog is that LA brown smog that we're actually familiar with and can see from Sage Hill School when we try to look towards the LA skyline. You usually see that brown haze. That's photochemical smog, and this is generally how it is forming. Now, smog, photochemical smog, tends to form and is more likely to form under much hotter temperatures. So when it's warmer out and the sun is out for longer, like in the summer months, you tend to see the formation of more photochemical smog. Okay. This should say thermal inversions. I'm sorry, not invasions. So thermal inversions, we're kind of moving on here from photochemical smog, but thermal inversions are a phenomena that can occur where instead of where our atmosphere normally goes from warmer air to cooler air as we move higher up into the sky, a thermal inversion actually changes that. A thermal inversion basically states that there's a mid-latitude layer that's relatively warm, and it traps layers of cold air below it because cold air is more dense, and it prevents the cold air from being able to rise. And the reason that's sort of a problem is because that cold air and the air that sits closest to the surface has the most pollution. So normally what would happen in a thermal inversion, and I'll show you with, or in a normal day, is those pollutions, the pollution would eventually rise because warm air rises, and then it would mix with other air in the atmosphere, and you wouldn't have this dense population of air pollution sitting in one place. But when you have thermal inversion, you do get all of this pollution sitting in one spot. So let's look at a couple images. So here are the normal conditions, right? It's generally warmer closer to the surface, and then we know as we move higher up in the atmosphere, higher up in altitude, it gets cooler and cooler and cooler. And because this air is much warmer and warm air rises, as the warm air is rising, it's taking all of the emissions and pollution with it, and it's mixing it with this colder air, and it's allowing for there to be less emissions sitting in one big spot. Now with thermal inversion, we have this cool air sitting down below, this cooler air above, which would be normal, but this is what's out of place. We get this warm layer, this inversion layer that causes this cool air to be trapped. It can't move past this warm layer. And as a result, this cold air, one, makes it much cooler where you are, and two, leaves all of those pollutants trapped in that city. And this can be a problem because this could lead to excess amounts of pollution, excess amounts of smog, and it can be hazardous for people who are breathing the air in this city. So how does this happen? How do you get this relatively warm layer, this inversion layer sitting right on top of a cold layer? It's common in coastal areas because of upwelling, right? So what can happen is if all of a sudden you have this burst of cold air coming from your coastal area, it can cool the area down here really quickly, but the air that has already started to rise still remains relatively warm, and as a result, you end up with this trapped layer. So anytime the city or the ground cools much more quickly than the air above it, that's going to cause that thermal inversion layer. You can also see this depending on the topography. So if there are mountains versus not, that can also influence when this formation happens. Okay, so next concept is acid deposition. Now, we've already talked about acid deposition a couple times. So acid deposition is acid rain, right? Now, acid rain, we said, are a result of nitrogen oxides and sulfur oxides being released into the atmosphere, the emissions of nitrogen oxides and sulfur dioxide. And again, those are things that come as a result of combustion of fossil fuels and things like that. And remember, acid deposition is a secondary pollutant. So nitric acid and sulfuric acid happen as those primary pollutants, sulfur dioxide and nitrogen dioxide, react with the air, right? And they form those secondary pollutants, so sulfuric acid and nitric acid. Those secondary pollutants then break down into nitrate and sulfate, and that's what causes that acid rain or that acid deposition. So let's take a look at this. Here's our primary pollutants, sulfur dioxide and nitrogen dioxide. They're going to react with our oxygen in the air and create sulfuric acid and nitric acid. And then those are going to further break down into hydrogen ions and sulfates and nitrates, and those sulfates and nitrates are what are going to actually come down as acid rain. Now, what's interesting, because we're talking about traveling here, a lot of the acid deposition that ends up falling down from the sky, a lot of the rain that we get here in the west coast of the United States, doesn't actually come from the emissions that we created. It doesn't come from our sulfur dioxide emissions or our nitrogen oxide emissions. Most of our emissions here on the west coast actually come from China. So the westerlies will carry that acid deposition from China all the way over to the west coast of the United States. And this could take days, it could take weeks, and by the time it gets to us, we're actually receiving their acid rain. And the same goes for us. A lot of the acid deposition that we're creating as a result of our emissions end up in places like Canada, right? So it kind of travels around. So really, by us decreasing our emissions, it won't actually decrease acid deposition in our cities per se, but it will decrease acid deposition across the world. So this is a really great example of why it's really going to take everyone in the world contributing to decreasing their emissions and decreasing their combustions of fossil fuels, because us making change isn't even affecting us. So we would hope somebody would make that change for us. So what are some of the effects of acid deposition? So in terms of agricultural land, we know that having too much acidity coming from our rain can lead to a lower pH and in our soil. And if our soil has too low of a pH, then our crops aren't going to grow as well. And farmers are going to have to add what they call lime to neutralize the acid. Lime is something, it'd be similar to adding like a pesticide or an insecticide, but it's used to neutralize acid. Lime actually will burn your skin if you're in contact with it for too long. It's incredibly basic. But acid rain, large amounts of acid rain will lead to having to add this to the soil. Aquatic ecosystems, we know that when the pH of water changes, that can affect the organisms that try to live in that water. We've heard of things like coral bleaching, which is increased amounts of acidity in the water. Terrestrial ecosystems, we know that plants can't survive as well if their pH of the soil changes. It can also affect the stomata, right? The opening and closing of the stomata, and that will adversely affect gas exchange. So that can affect the productivity of ecosystems. And then human construction, so specifically things like historical statues or buildings, can also be damaged by acid deposition. So things made of marble, which contain calcium carbonate, are susceptible to the damage from acid deposition as well. Okay, and that was the last big concept. So this was sort of a short one, but we'll go over a few review questions here. So high levels of photochemical smog are due to nitrogen dioxide, sulfur dioxide, and VOCs. So photochemical smog, high levels of photochemical smog are going to be a result of nitrogen oxide being broken down by sunlight into NO and O. And on those heavy days, it's going to be those NOs reacting with VOCs as well. So your correct answer here is D, numbers 1 and 3. Sulfur dioxide is what contributes to acid deposition, as does nitrogen dioxide. Recent increases in acid deposition in the western U.S. are due to increased emissions in the U.S., decreased precipitation due to climate change, increased emissions in China, increased precipitation due to climate change, or increased emissions in Europe. In this case, the answer is C, especially here in the West Coast. Most of it's coming from China. And that's also coming in from the westerlies, so our westerly winds. Okay, thermal inversions are increase the rate of smog formation, trap high concentrations of pollution at ground level, result in increased levels of acid deposition, are caused by high levels of precipitation, or reduce the negative effects of VOCs. The correct answer here is going to be B, trap high concentrations of pollution at ground level, because that cool air that's trapped below that warm layer can't move up, and that's going to lead to all pollution sitting in one area. And then acid deposition forms as a result of nitrogen oxides and photochemical smog, carbon monoxide and VOCs, sulfur dioxide and VOCs, nitrogen oxides and sulfur dioxide, or carbon monoxide and photochemical smog, and that should be D, which forms nitric acid and sulfuric acid. And then nitrates and phosphates, which eventually fall as acid deposition. And our last question here, the effects of acid deposition include increased cancer rates in aquatic organisms, decreased aquatic biodiversity, decreased mobilization of metals, increases pH of lake water, and decreases human health in impacted areas. And B should be your answer there, because coral reefs suffer, and coral reefs house most biodiversity. They're the most biodiverse ecosystems on our planet, so if those start to fail, it will decrease our aquatic biodiversity. If you have any questions on thermal inversions, photochemical smog, or acid deposition, let me know. But that was the end of this lesson. Have a great day.